You have joined, yeah?
Yes, yes. I managed finally. There was again a problem. Now let me see where the files are. Global selection. So, and what do you see now?
Yes, please share your file, then we will see.
1 second, so I hope it's this one. Okay.
Yeah, yeah.
Good. So I hope everything is working.
Yeah, it's working, sir. Yes. You can close it now for a minute or two, and then we will begin again.
But I'll leave it as it is. It does not.
Okay, okay,
Yeah,
sir.
yeah.
Okay, right.
And I kindly ask you, you start the session, and in case something is running improperly, please send me an email. I've also my mailbox open, so I hope everything will be okay today.
Yeah, I hope so, because last time it was
Yeah,
a big
really.
tragedy.
Really sorry about that, but I don't know until now what really happened. So
yes. So okay, we are up now. We begin. Sir, actually, I have already introduced you to the
good,
audience today.
good.
And the shortcut way was just to paste some message in the chat box. And yes, I think everybody would have read it. Okay, although the same thing is on also on the web page of this lecture. So Professor Hans Peter is Emeritus Professor and very senior professor in the field of the water management and water science. So he is a hydrologist, very renowned personality in the European continent. Not only Europe, is all over the world. Yes. So, sir, the forum is to you now. You please take over and you please add something about you as you usually do that correctly. I'm not really good in it. Thank you so much again, sir. And we all hope that everything will go well today.
I hope so.
So thank you again, and please, yes, please take over. Thank you.
Yes.
Again, yes.
So thank you very much, Hazrat. Welcome, everybody. So I'm here in Vienna, wonderful sunny afternoon, and it's a pleasure for me to introduce some of the work we have executed in the last years to you. So today I would like to address flood risks, and especially the emphasis would be what can we expect in the near and middle future. So I would like to start with general structure, including the objectives, then to somehow settle the scene. I will briefly explain some of the terminology I'm going to use, and then the topic starts with what do we observe so far with respect to flood risk, and what kind of approaches could be discussed, should be considered when we speak about midterm to long-term flood risk management. Okay, and I would like to address, would be probably very well known to you, some aspects of the European Flood Risk Directive. Then I would like to present one example about regional development, how we could include existing regional development plans in risk management. And finally, what kind of options could be considered when we speak about flood risk management. The latter part here, flood risk management options, includes only some frequently used options which should be considered. It's definitely not an exhaustive list. So I would say the overall objective of my today's presentation is the development of strategies to cope with flood risk in a changing environment. This sounds very simple, but I think it's a quite challenging task. So at the beginning, a few definitions. In general, when we speak about risk, we consider two features, or if you want, three. We speak about a hazardous event. This could be intensity of rainfall. This could be magnitude of a flood. This could be the intensity of an earthquake, whatever. So this is this Q symbol here. Then we have to think, what is the probability distribution with respect to magnitude of this event? So in general, we could say the more intensive the event, the lower is the probability of occurrence. And the third component refers to the consequences of something. So in general, risk has three elements: a hazardous event, its probability distribution, could be PDF or could be cumulative distribution, doesn't matter, contains the same information, and the consequences. So those three elements are needed to be assessed. What is a hazard? In general, a potentially damaging physical event that may have adverse impacts on societies, individuals. Depends on the scale how you are addressing the problem. What are the consequences? Usually we say damages, but not necessarily damages. Could be also number of injured people, losses in cultural monuments, whatever. So in general, are unwanted adverse consequences originating from the hazard and related to impacts on human life, health, property, or environment. And in general, we discriminate, when we assess the damages, we discriminate among exposure and vulnerability. Exposure is who and what is exposed to a flood event, in our case. So if you are living maybe slightly above the floodplain, then you are not affected directly by the flood, maybe indirectly. So we have to assess who and what may be inundated, for instance. And secondly, this is exposure. And secondly, how strong are the impacts on an individual, on an object, or something else? So how sensible is a person, an object, towards the hazardous event? How strong is the impact on that individual or on the object? So vulnerability in general is defined by the conditions determined by physical, social, economic, environmental factors, which increase the susceptibility of a community to the impact of a hazard. So this would be a quantitative expression of risk. And you see here the flood probability, then the damages, and you sum up over all possible events. And this would be the risk. You start at a certain level to sum up. It depends, could be the resistance of a levee, could be a natural inundation area, which is close to the river, whatever. So up above a certain threshold level, X star, damages start to occur. And when you think about the dimension of risk, then I think it's quite easily to be derived. The flood probability is expressed in probability in percentage of occurrence, and the damage function usually expressed in monetary units, or we come to that later on, also number of people who are suffering. So if this is a percentage and this is a unit in number of people or monetary units, then you see the risk is something like the weighted average. So it has the same unit, the risk has the same unit as the damage function. And you could say it's nothing else than the mean annual value of the consequences. This is the general definition of risk. What are the tasks for an engineer like myself? So we did a lot of studies on flood risk. We designed protective structures. We thought about rehabilitating floodplains to store water, etc. So in general, the task of an engineer, of a hydrologist, is to design flood protection measures. That's it. And then maybe to operate these measures. But how do we achieve design values? How are we able to estimate the probabilities? How are we able to estimate the damage functions? Well, we have data series, and first we identify the hazards. So what are the critical events? There are different approaches. When we speak about floods, usually we discriminate among annual flood series, where the largest flood in each year is considered as a hazard. But you could also think about partial duration series, where you choose a critical threshold level, and all the floods exceeding this critical threshold level are considered as a hazard. And then, considering that we have about 50 to 100 years of observations, then we try to establish models. And here we have, for instance, the dotted line on the left side would be the cumulative probability, empirical, and then we fit a model to that. Fitting a model means you choose an extreme value distribution. And there are a lot of different distributions. To cite a few, you could think about Gumbel distributions, Weibull, Log-Pearson, Log-Gumbel distribution, Wakeby distribution. So I don't know how many, but I would say around 20, 25 different models at least are available to fit a theoretical distribution to what you have observed. Now someone could argue and ask, well, why do we need a theoretical distribution? Well, think about, you have 50 years of observations. So you don't know really what you have observed. You have a series of 50 years, and you would like to know what is a 100 years event, what is a 1000 years event. probably you have not observed it in your short time series. So then you need to extrapolate. And for this, you need a model. Similar approach holds for the damage function, which I have here on the right side. So when we compare those two, we could say the larger on the horizontal axis, the event, the flood, the lower is its probability of exceedance. The larger a flood, the bigger are the damages. And somewhere you could think to design a protective structure at a certain level. We come to that later on. How to estimate this damage function? There are different ways. I could speak hours about that. Either you collect historic data, so you look back again, or you apply a hydraulic model to a certain region. You estimate inundation areas. You analyze what objects are exposed to a certain flood. You estimate the value of the objects, and then you establish these damage functions. But both are based on models. And we have now, you have seen it just previously, our probability distribution function. And then we define a certain probability. For instance, we are interested in 100 years flood event. So the probability that this flood event is going to occur is 1 divided by 100. So you would take here a probability of 0.99, and then you would get the respective design value. It depends on the country, but for instance, in several European countries, we say flood protection of residential areas should be designed at least for a 100 years level. Very densely populated regions with very sensible infrastructure maybe should be designed to a 300 years flood event or even higher. And then you derive this quantity from your past observations. You provide design values. And this is what you see here. What does that really mean? We look 50 to 100 years back, analyze the history, and then we derive measures for the future. And this is a very critical approach, I would say, because we assume that there is something like stationarity. The damage function from the past is also useful for the future. The probability distribution of the flood event derived from the last 50 to 100 years is also useful for the future. And even design values for spillways, for large dams, etc., they are designed usually for something like several thousand years return period. Think about that. 50 years of observations, then you extrapolate to several thousand years, and implicitly you assume all what you have observed in the past is something very close to what you will find in the future. Strange assumption. Now let's check about stationarity in our data. And these are reported changes in flood frequency. So the question is, are extremes becoming more frequent? And this is a graph from Munich reinsurance company based in Munich. And you have here different hazardous events. So geophysical events in red, like earthquakes, tsunamis, volcanic activity. In green, meteorological events like tropical storms, like convective storms. And in blue, hydrological events. This is interesting for us. So mainly flood events. And you see this period covers about 30 years, 35 years. And obviously, the blue percentage is increasing. So there are obviously more flood events now than in the past. Observation. So I've taken that data from Munich Re. What may happen with flood frequency in the future? And this is a publication from Hirabayashi, published in Nature Climate Change. And I think it can be easily understood. They analyzed how would look like a flood event of 100 years in the future. And you know, when you think about the future, it depends always on greenhouse gas emissions, etc. So they used here this RCP85 scenario. It's rather assuming an increase in greenhouse gases also for the future. But what do we see on this map? Where we have yellow and red areas, this means what is today 100 years flood may be up to the end of this century something like, well, 250 to 500 years flood. So the probability of occurrence is supposed to decrease. The blue areas indicate that what is today 100 years flood will be more frequent in the future and may happen, well, about in the average about every 25 years. So 100 years flood may become more frequent based on this climate change scenario. So obviously, the flood frequency is something which is under change and will substantially change in the future, by the middle up to the end of this century. What's about flood damages? So it has been mentioned by several authors that flood events are the most frequent and costliest natural hazards. In the average per year, a damage can be assumed to be around 19 billion US dollars per year. And more than 100 million people are suffering at the global scale per year from floods. And there is somehow a discussion about that, but the list here is quite impressive. It is assumed that in most of the regions of the world, flood damages have increased in the last few decades. And for me, it's somehow surprising because I know that in my country and in the countries around, a lot is being invested and has been invested in flood protection measures, such as implementing levees, building dikes, implementing reservoirs, flood retention reservoirs, etc. So also damages are assumed to increase. And this is again a graph from Munich Re about weather disasters worldwide, more or less same period over the last 35 to 40 years. And a red line refers to the overall reported losses, and the green line refers to the insured losses. So both show an increasing trend, and there are some exceptional peaks, year 2005, 2018. So definitely there is no steadiness, no stationarity in the data. And several of these events have been analyzed in very detail, and it's concluded that the increase in damages can be attributed to a growth of population in flood risk areas. And well, people are getting richer, communities are getting richer, so a higher value is exposed to flood events. Let's briefly summarize what we have discussed so far. We have changes in the flood frequency, and obviously we have changes in the damages. So, and we should consider these changes in time. So from a mathematical perspective, we should write here a revised equation that the flood frequency is dependent on the peak as well as on the time. Damages are dependent on the peak as well on the time. And this would be a quite a difficult task. So I have here chosen 3 approaches how we could handle that problem. Updating procedures, scenario-based approaches, sensitivity-based approaches. Because I tried to show flood frequency has changed and will change. So let's analyze these approaches in some more detail. And first I start with the updating procedure. And for you who live in Europe, I think it's obvious. I have only 4 or 5 slides for this. We have to think about the flood risk directive, and the flood risk directive agreed in the European Parliament in 2007. As you know, has to be ratified in each country. So in Austria, I think it was ratified 2010. So since about 2011, it became effective to be applied. In general, the flood risk directive provides a framework for flood risk assessment and flood risk management to reduce potential adverse consequences. And this somehow constitutes a priority list with respect to human health, the environment, cultural heritage, and economic activity. Everyone can still hear me? It's okay? Hello?
It is fine. It is all
okay.
All okay. Yes, please.
Thank you. So, and the flood risk directive should contribute to reduce existing risk and avoid the emergence of new risks. Sounds good, but also quite a difficult task. It is a basin-wide approach, so it's very essential, and also public participation is somehow a need at all levels for implementing the flood risk directive. And how is the flood risk directive being executed? So it is agreed European-wide that inundation maps have to be provided in each country for 3 different events. I dislike somehow that only one event, 100 years flood event, is legally binding. The other 2, a frequent flood and a very rare flood, is differently defined in European countries. And when you think about that, river basins, many of them are transboundary basins. When you think about that, rivers very often constitute borders, left riverbank and right riverbank, different countries are being located. It's creating somehow a problem when on the left side of the river, they have different standards than on the right side of the river. It's somehow mitigated by the fact that, as I said previously, a basin-wide approach is needed. But 3 different inundation events have to be delineated. Then areas of potential significant flood risk have to be identified. There are criteria for that. Those who are interested in can easily find it in EU homepage. Then we have for all our rivers maps which describe the flood risk, and then we have for all river basins flood risk management plans. And these management strategies have to be reported, have to be published, have to be transparent, have to be assessed after a certain period, and probably revised. Also, I think very interesting, non-structural flood protection measures are emphasized, if possible. See, an example like in the Netherlands, giving room to the river. In my country, we speak very often increasing natural retention capacity in basins. And very important, the updating procedure for the implementation. And this is what you see here. So we started in 2011 with coming up with preliminary flood risk assessment for all EU countries. Then 2 years later, flood hazard and flood risk maps had to be ready, 2013. 2 years later, flood risk management plans had to be ready to reduce identified risks and to avoid the emergence of future risks. And this is a process which is repeated every 6 years. So in 2018, new flood risk assessment, hazard maps and risk mapping maps, 2019, and we are now already in the second phase where the new management plans are relevant. So every 6 years, the cycle is repeated. And this, I think, is quite a benefit because we can learn about changes in land use, we can learn about changes in flood frequency, whatever possible impacts of climate change. Briefly summarizing the flood risk directive, I would say it's a transparent approach, it's a basin-wide approach, it's based on public participation, although it depends also on you, would be a point for discussion. I see some deficits really in broad involvement of the public and in sound discussions, but everything can be improved. Also, a point which can be criticized is there are other European directives which are related to water, and they are not fully harmonized. It's an adaptive approach, but still it is not an anticipative approach. We don't look ahead. We always identify what has happened, where are problems, and then we develop a new plan. But we are not looking ahead. And this brings me to the next point, that we try to apply a scenario-based approach to identify and assess emerging risks. And I would like to give an overview of an application we did for a provincial government in a province of Austria. We started with assessing the recent flood risks for 3 different events. So now, okay. Then we were looking for population changes. Then we assessed the future potential according to regional development plans, and they are available also at the European scale. You can find them. You can have a look on the publications from European Environmental Agency, this former Prelude project, and also, how is it called now? Transition Now, I think, also from European Environmental Agency. And then we assess the sensitivity of the damage potential with respect to magnitude of the flood, because we don't know what will happen. And a simplified example. We start with existing conditions. So we have here, let's say, a residential area. Here is a river, and you see 3 different inundation areas. For Austria, it's a 30 years, 100 years, a 300 years flood. Today's situation, the colors here indicate only different types of objects, maybe small houses and large houses, whatever you have in mind. Recent situation. And now you can assess the probability of damages, you know about the exposure, what and who is exposed, and then you can come up with a damage function. And then we look ahead, let's say up to 2030, how it may look in about 10 years. And you see, there might be a development in this designated area. If people move in, there might be more houses. Damage, given the same flood magnitude, would change. But we could also think about climate signal. What happens if, due to climate change, the flood peaks would change? And you could assume a delta Q. This is done in some countries at 10, 12% or something, and only see what would happen. Nobody says it will be plus 10%, but you can learn how sensitive is something. And this has been applied for a large region. We have flood maps for 30 years, 100 years, and 300 years flood. I've chosen here subsection that you can see something, and you see recent damage potential, which objects are endangered with different probabilities. Starting point. So this would be the recent flood risk, characterized by here the area of buildings in the floodplain. We did also different assessments, but here, how many buildings and what is the area of the buildings being located in the floodplain, and this analysis has been executed at a lower level than the district level. So you see these, well, areas here, these red, blue areas, purple areas indicate a very high recent risk. Top. Green areas, no flood risk, and yellow, very low flood risk. Situation today. Now, we assume and we analyze demographic changes, and we look what might happen. And you see, this is the same region, and these are the demographic changes until 2030. You find that also at the European level and at each national level. You can easily see, here is Vienna, our capital, and you see around Vienna, people move in. Here is the provincial capital, an industrialized area, people move in. That's another larger city. You see around the city, number of people increases. And the blue areas indicate there will be less people in the future. So national migration, people from that rather agricultural areas with lower income, they move towards the centers. So when people move in, then there is a higher damage potential in the future. And this can be assessed, and these demographic changes are quite reliable data. So this would be now the situation due to population changes. And again, these areas here indicate emerging risk. So here the risk will increase. We have existing risk. We know about emerging risks. You can combine now those two maps, and I don't want to go into very detail because there are many ways to do that. But you see, there is a nice overlap. So here the existing risk is quite high and the emerging risk also. So you can easily derive something like a priority list. And this would be that map, what you see here, has been composed by combining existing risk and considering internal migrations of more people are in here, there. So you see where sensible areas are. And in the next step, you could say, well, what happens if the flood peak changes due to climate? It's up to you. You have, for your regions, a lot of information. So here we only display what happens if the flood peaks are getting higher. And you see that in the area where we have already a high existing risk, flood risk is not relevant. In some other areas where we have today a lower risk, these areas are maybe more sensible to climate change than other areas. Inundation would be larger, more people might be exposed, damages would be higher. Conclusion, I tried to show for this example using scenarios and using sensitivities to show where we have today a higher flood risk, where we may expect an increasing risk due to migrational patterns, and which areas are sensible with respect to climate change. And when you analyze what has happened so far, you could easily say increase in flood damages is mostly due to conflicts between land use planning and risk planning, flood risk planning. So there is, in my country, and I would say in other countries too, a gap which needs to be closed somehow, to harmonize risk maps with regional land development plans. And what we have found so far is that the development plans have a stronger impact on the damage potential than the changes due to climate. But this depends on the region, so it might be different in other areas. And as I tried to show, we provide information to identify hotspots, to identify emerging risks, and to rank somehow these aerial subdomains. And in my last part of my presentation, I would discuss options for risk mitigation. And as I said at the beginning, it's not an exhaustive list, but I think it could be stimulating to expand it and to see where actions could be taken. So this is the expression of risk. So the damage function, the probability of an event, and this is the risk. So one point could be reduce the damages. What could we do? Well, for those buildings which are located in the floodplain, they could revise the building codes somehow to reduce the vulnerability of objects in the floodplain. Second approach, harmonize risk maps with regional development. So we found in some regions that the regional development goes in direction of flood risky areas, and we presented that to the local administrations to maybe to revise their local development plans to avoid the emergence of future risk. Another approach could be to implement early warning systems. So in the meantime, we have more or less for the whole territory of Austria, early warning systems. I think the forecasts work quite well, but still I think there is some training needed for the people who live in the floodplain and those who might be exposed to floods. So raise the awareness about their risk exposure. Avoid secondary damages. I will not go into detail, but it means that some sensible infrastructure, for instance, in a company, is, for instance, based in the basement, energy supply, whatever. And this is the first part of the building which is being inundated. You find also new settlements in floodplains. This should be avoided. Another strategy which is actively applied in Austria is resettle people outside the floodplain. So mostly agricultural areas, farmers can still keep their land, but their houses should be built somewhere outside the floodplain, and monetary incentives are provided to motivate the people to resettle outside. And also there is a large uncertainty in the changes with respect to time and in loss functions in general. So also some improved assessment of the damages could be helpful. This refers to damages, it's not exhaustive. Think about changing the flood frequency. So, for instance, one way could be increase the natural retention capacity. In some areas, we did a study in southern Morocco about that, and there it looked quite an optimistic approach to store the flood water and to use the flood water in some areas for groundwater recharge, so the water could be subsequently used during drought periods. Reduce the uncertainty in the probability distribution, and think about, I will not touch this point today, about direct human interventions. We channelize our rivers, we cut off floodplains. This means we reduce the retention capacity, and for the downstream people, floods are sometimes slightly increased by human activities. We can build, for instance, here a flood detention reservoir. So this is the river, here's a reservoir beneath the river, and a flood is stored here without inundating the residential areas. This is the protection level, existing protection level, whatever it is. And, you know, I have a few slides here about levees. Somehow engineers like it to build levees. I'm not always a friend of that, but it's one of the options. And you see, this is a photo from Austria, I think 2002. Here, probably you can see it, but here in the back, there are the blue light teams, emergency teams, and here is a levee. On the left side is the main river, and the levee has collapsed without being overtopped. So you could say the Austrian engineers, they are not able to build sound levees. I have here one example from Shinkawa River in Nagoya City, Japan. You see the levee broke, and Nagoya City, about 6 million inhabitants, was flooded in some areas up to 6 meters. Could say, well, Japanese, they are not able to build a sound levee. So an example from United States, New Orleans. The levee broke. By the way, there is, if you are interested in, a nice song from Bob Dylan, ring the bell, the levee's gonna break. So it happens more or less everywhere. So there's a probability that protective structures are failing. Then we have temporary protective structures, as you can see here. So there are different technologies how to implement them, but they are only functioning and only in operation during a flood, and then they are removed again. And they work somehow quite well. This is an example also from Austria along our main river. Not that costly, but it requires a good early warning system to build it up quickly. Another way is to increase the levee. This is an example from China. And you see, this is the levee from 1945, and this is the levee from 1946, and the levee from 1947 and 49, and this is how the levee is today. And can easily think about what would happen in the next 30 years. So probably the levee is being raised. In the first step, it sounds reasonable because you protect here the people. In the second step, you have to think, you cut off inundation areas, so you transfer the flood problem downstream to someone else. And what I really like, it's not that frequently implemented. You see here on the left side a river, here is the levee, and on the right side is the hinterland. And like any larger hydraulic structure where you need a flood release structure, you should think about designing sections of the levee for overtopping without destroying the levee itself. You have a control process, and if the design level is exceeded, you start slowly to inundate the hinterland, but in a controlled way. And when we somehow briefly summarize these options, we could say strategies are needed to work in the short term and the long term. We should think about a sound hazard communication to the people who live in the floodplain. They should be aware. Somehow I have several times proposed in some villages to draw a right line along all the houses where 100 and 300 years flood will be, to convince the people that it's somehow a dangerous and risky situation. I also think highly vulnerable objects should not be located in the floodplain. You find hospitals being located in the floodplain. Even I know one case where a flood warning system is being located in the floodplain. Kindergartens are found in floodplains. Chemical firms. So might, in that case, hazardous chemicals might be released to the environment. They should be removed outside, definitely. We should improve the capacities of safe overtopping of the levees. So we should integrate spillways into the levees, and behind the levee, people are not safe. They are safer than without the levee. But there is still a residual risk that the people living here in the floodplain are exposed to an extreme flood event. And this means also the land use patterns behind the levee should be elaborated in close collaboration with risk managers to avoid the emergence of future risks. And, well, improved forecasting systems would be also helpful. summarizing my presentation, the task was to think about risk management strategies in a changing environment. And I tried to show you that frequency is changing, land use is changing. So we have to think about that. It's not an academic question, it's a question of daily life. The flood frequency are sometimes already visible, but mostly at a smaller scale. When you analyze larger basins, it's getting difficult to say flood frequency is increasing, decreasing, but you remember I've shown you also what might happen under increasing greenhouse gas emissions. More quickly than the flood frequency changes the damage potential. And due to these two changes, we propose that we use adaptive approaches, that we test different scenarios to see, does our flood protection system work properly? And we should also think about the sensitivity analysis, somehow analyzing what happens if the flood is 10% higher, etc. And overall, flood damages are really a serious threat for society. They are increasing. We have a broad scope of actions, and we did also some studies about that. Higher levies result in general, due to modified land use behind the levee, in a higher damage potential behind the levees. So this means, in other words, the probability that something is going to happen is reduced by the structure. But if something happens with a very low probability, the damages will be much larger than today. And non-structural measures like re-establishing retention capacity in a basin, re-establishing wetlands in a basin, etc., might be a very helpful approach. So thank you very much for your attention. And I'm looking for questions. Thank you. Hello?
Yes, sir. Thank you so much.
Okay.
Yes, we invite the audience for their questions. Please come forward. Yes. Any question? Any question?
I think something is quite well known, what I said about the flood risk directive. And you know, you go to your computer and easily you can find all the inundation maps, all the risk hazard maps, all the objects which are exposed to 3 different floods. They are online accessible, and that's already something. And the updating I also highly appreciate. Still, we could improve it.
Yes, sir. All right. Sir, can you please close the slide?
Yes. How to do it? Escape. So, yes.
Yes. Yes. Yeah. Right. Yes. Okay. Any question? Any suggestion? Any comment? Please.
Don't hesitate. Therefore, we meet. I would be pleased to meet you personally, but not possible.
In your lecture, sir, especially the national university, Ukrainian University of Water and Water, yes, water and water management. Actually, was very interested in your lecture particularly, and we see several people have joined from the same university today. Yeah.
Very pleased to know that you are attending. You're living under extreme difficult conditions. In the past, I had the pleasure to visit several of your universities. I was also at National University, and I was in Odessa, in Kharkiv, in Lviv, in Kiev. And last year we had a summer school in Yaremche, close to Ivano-Frankivsk.
I think on the water sciences and water engineering, this is the premier university in this country. And hopefully some of the scientists will contact you after this.
Yes. Yes.
Okay, please, any question, or you can write here in the chat box also.
Yes.
Okay, fine. If there is one question, please read.
Yes.
Yeah.
What computer program do you recommend for flood forecasting? You know, there are numerous models available. I would say when you're looking for a model, you should think about the general settings in your case. So is it a large basin? Is it a small basin? Do you have torrents, or do you have rather lowland areas with huge flooding, and then the flood propagation might be more relevant? So for Austria, as you know, it's rather hilly country, and we develop, and in our case also snow melt is relevant. And you know, we have developed for many basins online systems, so they are operated by the regional authorities. They are running day and night. So we get, the process is the following. We get the general weather forecasts from UK, from the Reading Center. These general forecasts, which go up to 72 hours, ensemble forecasts, so you get different forecasts for the next 72 hours, are downscaled to our regional settings by the Meteorological Service of Austria with a grid resolution, don't know what the recent one is, something like 2 kilometers or 1 kilometer already. So we have at 15 minutes time slices, 1 kilometer grid, weather forecast for 72 hours. And these forecasts are automatically uploaded to the hydrological system, and the hydrological system provides forecasts at agreed locations along the main river course, and also, if necessary, along tributaries. This hydrological forecasting model has been developed by ourselves. It's fully available, documentation is available. I don't want to convince you that you should use it. If you are interested in documentation, could be a starting point to read if it's useful for your purposes. We have it applied in many different regions within Europe, in Greece, in whole southeastern Europe, for the whole Danube basin from the spring down to Bratislava, so about more than 100,000 square kilometers. We have applied it in the Ob River basin, in Siberia, in the river basin of Niger in sub-Saharan Africa. We have applied it also in Venezuela, So far it worked quite well. And if you are familiar with hydrological modeling, it's quite a flexible tool. So we could provide that, of course, to you if you want. Maybe I need some time to do that, but it's publicly available.
So it's great, sir. Let's close this session now.
Okay.
It was really wonderful, and revealing lecture. Everybody would have enjoyed it, I'm sure. Sir, next time we will definitely meet, maybe in the month of September, as I have written to you.
Yes, you're
So,
warmly welcome, Hazrat. So
yeah,
yes,
yeah.
it depends when you come, but maybe we find an option. If you want, maybe you can stay in my apartment, or you can stay in my farmhouse. We need to discuss it when times.
Yeah, we will do. We have the time. I will write to you in advance. I already have written couple of emails. So
Yeah.
one other email, I think you will reply to it. But please, next time when you reply, so I will request your phone number so that I can quickly
Yes.
contact you. Okay.
Yes.
Thank you,
Yes.
sir. Thank you for your support and help. Always you are very kind and very helpful in all the things. So thank you, the audience. Also, you have taken a lot of interest in this particular lecture as well. So thank you again. We will meet day after tomorrow on 17th June. There is the last lecture of this series, May and June series. So after this, we will have the lectures only in the month of November this year. And from the next year, we will be changing some format of this program. So thank you once again for, everybody has taken the interest and contributed. Thank you, sir.
I thank
Thank
you
you,
all.
sir.
Thank you very
Thank,
much.
thank
Bye.
you.